Hi, today I'm going to start to talk about frames. Up to this point we were talking about the truss, which is kind of a structure we use for um, building like at bridges. And if you remember, we will say that the trusses was like the two element point that connected to joint like that. So if I have something like that and then the simple truss, and I will say that we have the elements that are connected by the pins together, and there are going to be the forces only applied for the joint. For example, I have only force here, and all the members in this structure are going to be two member forces. So it means that the forces, the internal forces in each member is along that. Otherwise, because we have only forces applying on the joint, the force apply on 2 points of these members, and therefore the internal force is going to be along that. So if, for example, I have the A, B, and C here, so the force in the AB is going to be along the AB, the force in the AC is going to be along the AC, and the force in BC is going to be along the BC. Now, another type of structure that we have is going to be frames. That frames is a type of a structure that not only loads can be on the joint, it can be on the member as well. For example, assume here as a very simple frame, so it's going to be simple like that. So I have an element like that, and then I have another element like that, and assume these two are connected both by pin. So also they are connected here by pin. And in this case, the load we have is not going to be only on that member. For example, we may have some load applied on this member here, and we have some moment applied on this member here. We may also have or we may not have forces on the joint. So unlike the truss that you have the two member forces, in these cases these are not the two member forces. Remember, frame might have, might not have two member forces. So for this simple one, if you look at that, this member has if I put the let's say if I put the so it's going to be a x and ay, and it's going to be by bx. So we have forces applying, and so we have forces at that joint. There are some forces, it's going to be internal forces there, so we have some forces here, and we may also have that external forces like that there. So it's combination of forces applying on that frames. Because of that, the elements might or might not be two element forces unlike the truss. So now we need to do a little bit more analysis on that. Most of the time, for example, if we look at here, what we have four unknown as the for the supports, and we have some external forces apply on that. And if you look at that, uh, for example, we cannot find any of the supports because we have four unknown, and we have only three equilibrium equation. Similar to the truss, one method we do that, we disassemble the truss and we try to work on what's happening in that truss. The same thing we do that here. So for example, here also we will do the same thing. So if we have the A, B, and C, similar to that, we will go ahead and we'll disassemble this truss into the joint AB, into the member AB, and to the member ABC. So I'll go ahead and say this is my member AB, and then this is my member BC. So if I call that, so it's going to be A, this is going to be AB, and this is going to be BC. Not similar to what we did for the truss. When disassemble it, we will put all the external forces on those members first. So we'll go ahead and put all the external forces there. So I will put first the support there. So we have the AX, have the AY, and we have the BX, and we have the BY. Also we have the external forces. So these are the supports. We have the external forces itself. So we have one force here, and the force on the joint might be there. And then we have this moment. So for a moment, assume there is no forces on the joint, so it's gonna make it yeah, just simpler. So assume there is no forces there. So we have only forces on the member. So just to make it simpler. So assume there are no forces there. So go ahead and assume no forces is there, and then these are had, and then we are gonna have the internal forces. So if internal forces in this case, if I want to put this, so I'll have that here. I have internal. So what are internal forces? So assume I have two internal forces here, and I will put it here. Assume as a bx and by, and whatever I put on this joint, I'm gonna have it on the. I have the opposite of that there, so it's gonna be bx and by as well. So this is the by and this is the bx. Now I have two members of AB and BC, and how many unknowns I have? So I have AX and AY, two here, BX and BY, two here, and sorry, these are the CX and CY. So I also have the CX and CY there. So these are CX and CY. So I have CX and CY, CX and CY there. So I have AX and AY, two unknown here, BX and BY, two unknown here, and CX and CY, two unknown here. So in total, I have six unknowns. I can write three equilibrium equation for AB. So if I go ahead and say that for member AB, so for member AB, I can write sigma fx is 0. I can write sigma fy is 0. And write sigma m is 0 about any point. So these are what I have for member AB. The same for member BC. I can write sigma fx is 0, sigma fy is 0, and sigma m is 0. In this case, I have three equations here, three equilibrium equations here, three equilibrium here. So six equations in total, and I have in total six equations. I can find all the unknowns. So this is mostly the way we are doing it in when we are dealing with the frame. So we just disconnect the frame, and we have the all the external forces, all the reaction forces, and then all the internal forces on each member. And after that we will start to write the equation for each member. So write the equilibrium equation for each member, and then eventually solve all of them together. If we have the forces applying on the joint, also we have to write like what we did for the frame. For the truss, we draw the joint and we put all the forces on that joint. If we have the force applying on the joint as well, so in addition to drawing that, we draw the joint and we draw the forces on the joint as well. So it just make it a little bit more difficult, but it's not that bad. One thing that I want to mention about this is that if we dealing with the when we are dealing with the frame, What would we do if we have pulleys and ropes? This is what I want to show how we will do that. So let's make some space here. So if you have a pulleys and rope, and for example, assume I have rope, I have a pulleys like that, and then I have a rope going through that. Then I have a weight here. So if I have this kind of, most of the time when we are doing that, we will cut the rope and assume, and then we draw the free body diagram of that. So how it's going to work is that, again, I'm going to have the pulleys, and then I cut the rope and draw the rest of the. So if this is my rope, so I will cut the rope. I will cut the rope here, and then I will put the tension there. So it's T. It's going to be T. The whole point is that whenever we have the pulleys and rope, we cut the rope, and when we cut the rope, there are 2 points. First of all, the tension in the rope, as long as we have the same rope, is always stay as T. So it's the same, whatever is that. It doesn't matter what direction it is. The magnitude is always a T. And the second thing is that the force is always as a tension. It cannot be compression. So it's always pulling the rope away, and it's always is going to be along the rope. So regardless of what direction it has. For example, here let me draw an example. Assume uh, um, assume I have a frame connected to the wall, and then I have a pulleys on the head of that, and that pulleys has a rope that also connected to the wall, and then it's uh, pulled away with the force P here. And I want to draw the free body diagram of that. So what I'm going to do is just draw the whole thing here. So I will draw my frame. I remove it from the support it has. I draw the pulleys, and then I cut away the cord. So I have the cord is going to be here, and it's going to be here, and then on the cord, and I will put all the forces I have. So for example, here I would have the tension here, as again it is along the rope. I would have a tension here. It is going to be along the rope. So both of them are tension. Both of them are along the rope. And also I have here, if this point is A, if I consider this point as A, then here I would have AX, AY, and M at A. So these are the reaction, these are the force. So most of the time, if we have the pulleys and we want to do the calculation, this is how we do. Just cut the rope and add the tension, and as long as it is the same rope, always the tension is equal, the magnitude of tension is equal. It doesn't matter the direction of the rope. So if it's T on one end, it's going to be T in the other end, or in any place along that rope. And it's it is the magnitude, and also is always along the rope. It's always along the rope. It's always tension. So and then you can do the calculation for whatever we did. Okay, now let's look at an example. Assume we have three pulleys that are connected to the ceiling like that, and they're connected to each other by the ropes. And uh, the first one, the pulleys is having the 100 Newton weight, and we want to find the value of P that hold this whole system in equilibrium and how we are going to do that. So remember, when where we have the pulleys, we're going to just cut them away and separate them and start to consider them one by one. So I will go ahead and first of all I will cut away that very first pulley. So I will go ahead and cut away the pulley A at that point. So if I cut it away and the pulley is A, so this is what I'm going to have. So this is the pulley A, and here I have the weight of 100 newtons. So the color. So I have the weight of 100 newton here, and then I have my rope that is caught in that point, and there is a tension in there, and also as I would say T and T. Remember, it's the same rope. Because it's the same rope, the tension is going to be equal. Whatever the tension is here and it's gonna always be along the rope itself. So if I write the equilibrium equation for this one, and then what is I write sigma Fy is 0, what I will gonna get is that the 2T that's going upward minus 100 newton is 0. So therefore the T would be 50 newton. So the T is 50 newton. So I have the T, the tension in the first one. Now I would go ahead and I would isolate. I cut it and isolate the second pulley, the pulley B. And how I'm gonna cut it? I'm gonna cut it like that. So I cut it away and I bring it out here. So it's gonna be the pulley B. There's a B. And then I will put all the forces I have. So I have the ropes. I will put the cutting the rope I cut. So there's one, I cut it here, and there are two I cut here and cut there, and then I will put the forces on those rope I cut. So if I go ahead and put it here, it was the force here is T. So this is the T. This was between both of them. So it's the T here and it's going to be T there. So it's a T, and we know it's 50 newton. And look at this rope. This rope is going all the way around C, then goes all the way around B and go there. So it's a single rope from that end all the way to the P. So whatever tension I have in that rope is going to be the same all the way along. At any point of that rope that I considered, is going to be the same force. So if you look at here, the tension in that rope is P. So it's a P here and a P here, P here, and P all the way, because we are pulling it with the P. So the tension in that rope all the way is going to be P. So it's going to be P here and it's going to be P here. The same. So if I go ahead and write the sigma Fy here equal to 0, again what I have is 2P minus 50 newton is going to be 0, and therefore the P would become 25 newton. So if you look at this system we could have just simply have the 25 newton, and by that 25 newton hold the 100 newton weight. It basically we use half of that force to get to it. In case that we want to know how much we have reaction here, what's the reaction at point C, what we can do is that we can go ahead and disconnect this pulley C from here and draw the free body diagram of that. So I will do that. So if I come here and draw the pulley C, and then what I have here is the I have the ropes, the two ropes that I would cut them, so both of them going down, and then I have the the support here itself. So I have that support part also, which is I cut it through. And the forces I have is gonna be here is P downward, here is a P downward, and then here I have the R. And then if I write this sigma Fy for the C, if I write sigma Fy is 0, then I have R minus 2, and the P is, we know that P is 25 newtons, so 2 P is 0, so R minus 2 times 25 is 0, therefore R is gonna be 15 newton. So if you look at that, this whole system, we look at here, we have the 100 Newton weight. We only need 25 Newton to hold it, and at this point, at this reaction, is going to be 50 Newton. So that's how the pulleys work. So remember, whenever you have the pulleys, just disconnect them. And remember, as long as you are on the same rope, the tension in the rope is the same. The force in the rope is always tension, and it's always is along the rope. So it's always pulling the rope, no matter how we are looking at that. The internal force of the rope is always pulling the rope. Okay, let's look at another example. Assume we have a frame like that, so it's the A, B, B, C, and C, D, the three members connected to each other, and there's the fixed support here, there's a roll, there's a pin support here, and we have the distributed load, the triangle distributed load at the top member. I want to find the reaction at A and D. If you look at here, because it's a fixed one, we have 3 reactions at the A and we have 2 reactions at D, so in total we have 5 reactions, and there's no way that we can write the equilibrium equation for entire frames to find those reactions, because we can only write 3 equations, 3 equilibrium equations, and we are going to have as you can see here, we are going to have 5 unknowns. So I will first I will put the reaction there. So I will go there and says, okay, this is the, in the A you have the A Y, have the AY, we have the AX, and we have the M. Also at D we have dy and we have dx. At dy and we have dx, and we can find. Now, before I move forward ahead and write a further equation, that's one thing that I want you to look at. That here at this point, at this one, if you look at the D, C, at the member CD, there's only force at the C and only force at the D, and there's no moment, no nothing there, because only we have force at C and only we have force at D. It's going to be a two-member forces. So instead of writing the D like that, we know that because the two-member forces, that forces is going to be along the CD. So instead of doing that, we can just remove that and say that that force is going to be along that member. Whatever is the dx and dv is going to be along that member. So I'm going to leave it here, but eventually when I separate it, I put the force along that, so you will see that how it will comes out. So that's going to be what in our reaction. Don't make confused, it's not going to be the correct for the AB, because on the AB we have the moment, although we have the force at A and B, but we have the moment, and because we have this moment and this moment can be applied anywhere, therefore it's not going to be a two-member force. So AB is not two-member force, only it's the CD is. So I'm gonna write, I'm gonna because we cannot find the reaction the way it is first, so I'm going to just disconnect these into all the members. So I'm going to disconnect it into the AB. So it's going to be of member AB. So that's the AB. And then we have the BC, member BC. And then we have the member CD. So it's going to be A, B, B, C, and C, D. Now I'm going to put the external forces. The only external forces we have is this 100 Newton distributed, 100 Newton per meter distributed load. I'm going to just replace it with the resultant force. So we know that the magnitude of this distributed load, the magnitude is equal to the area underneath of that load. So whatever is the area of distributed load is the magnitude of that. So the width of that is 3 meter. So it's a triangle. So this side of triangle is 3 meter. This side of that is 100. So we have 100, we have 3. So that force is going to be, if I put it here, is going to be 1/2 times 100 times 3. So that's the force we are going to have, and it's going to be 150 newton. So that's the force there. And then where it's going to be applied is that we know it's going to be 1/3 from the base, from the base. So basically it's going to be look like that. So that force is, this is the 3 meter, so that would be 2 meter, and this one is 1 meter. So the total is 3 meter, and we know it's going to be applied 1/3 from the base. So it's going to be, the distance is going to be 1/3 of the 3 meters is going to be 1 meter. So it's where that force is going to be applied. Have the AY, have the AX, and we have the M, the moment. Here, because it's the two member forces, whatever is the reaction is going to be along that forces. So instead of having the dx and dy, we are just going to replace it with the single force, because it's going to be two member, it's going to be along that member. So it's going to, I will assume it might be tension, might be compression, we don't know, I just put it like that. So I will just put it FCD. So whatever is the magnitude of FCD is equal to the reaction of that at point D. And here the same, we are going to have the opposite of that, so it's going to be FCD also here. For the point B, it's not going to be like that. So and the same there, if we have it going there, we're going to have going the opposite one also, FCD going there. And here for the B, we have the BY and BX, and don't worry about the direction, just choose the direction and put the opposite of that on the other side. So it's going to be BX and it's going to be BY. And this theta, this is the angle theta we have, that's this angle of theta, this force, because it's going to be along the BC, always has the angle of theta, and the same here, we will have this angle is going to be also, this angle is going to be theta. Now, before we can do any calculation, we need to know this angle theta to do our calculation. And to do that, if I come here and look at this, let me show it here. If I come here and look at this triangle here, this triangle here, if I look at this triangle and try to get the theta from that, so I draw that triangle here. And this is the theta. And I know in that triangle, this is 4, this is 2, and this one is going to be 4 square plus 2 square, which is going to be equal to 20. So the theta, if I want to write that, so I know that the cosine theta, right, that the cosine theta is this side, the cosine theta is 4 divided by square root of 20, and the sine theta is this side is 2 divided by square root of 20. So now we have all the information we need, and we can go ahead and start to do the calculation. So let me draw the line here, and then now I will start with the member to do the calculation with member BC. So let's start with the member BC first. So if I go ahead and say member BC. So if I do the do the calculation for member BC, if I look at here, probably if the very first thing I can um, um, calculate, because we have the, if I write the sigma fx, it's not going to give us anything because the bx is unknown and fcd is unknown. The by is also not going to give us anything. So I start to write a moment about point B. That's probably the best thing I can do. So if I write sigma m about point B is 0. So if I write a sigma m about point B, why I doing that? Because I write about point A, the bx going through point B, the by going through point B, so they don't produce any moment. The only forces produce moment is this force here, the resultant of the distributed force, and the FCD, the vertical component of that. So if I go ahead and write that, what I would have that the FCD has two components, is the vertical one and the horizontal one. Again, the horizontal component of FCD goes to point B, so it doesn't produce any moment. The vertical component of that is the FCD, and if this is the theta, the vertical moment of that is FCD sine theta. So it's going to be, again, if I write that, it's going to be FCD sine theta, and we assume the counterclockwise is positive. So FCD sine theta, so that's that's the force we have, and the distance from C to B is just 3 meters, so it's going to be times 3. And when we have that, if you look at that, about point B is going to rotate it counterclockwise, so it's going to be positive. The other force we have here is this 150 Newton, and so we have the 150 Newton, and the distance is at the normal distance between this force and point B is 2 meters, so it's times 2. And if you look at it, about point B, it's going to rotate the beam clockwise, so it's going to be negative. And we don't have any other forces here, so this one is going to be 0. So therefore, if we solve that, the FCD comes out as 223.6 Newton. So that's the FCD we have. Now we can write either sigma Fy or sigma Fx. So if I write sigma Fy is 0, so what we have here is the By, is a negative By. And then we have negative 150 Newton, this force here, the resultant force, negative 150. And then we have the FCD, the Y component of FCD, positive, so it's going to be 223.c times sine theta. That's all we have here, so it's going to be 0, and then if we do the calculation, the By would be negative 50 Newton. And then we will write the sigma fx is 0. And if you look at the sigma of x, we have the negative bx here, the negative bx, and then we have the x component of fcd, which is going to be negative fcd cosine theta is 0, and we know the fcd is 223.6. So if we solve that, the bx would comes out as negative 200 Newton. So we have the sine theta and cosine theta here. So anywhere here we need the sine theta, cosine theta, we use it from here, and the FCD is already, we have it there. So we'll get we get the FCD, so we get the force in that member, or basically we get this reaction here, and we get the Bx and By. Now only what we need, so we from how many unknowns we have? We had 3 here, 2 here, and 1 here. We had 6 unknowns, and from all these 6 unknowns we already get 3 of them by writing the equilibrium equation for member BC. So we know 3 of them, and the 3 left, so the 3 is AX, AY, and M. So we'll go ahead and write the equilibrium equation for the member AB. So if I go ahead and write the equilibrium equation for member AB, so what I would write there is that I would go ahead and first of all I would write the sigma of x is 0, probably is the easiest one. So if I write the sigma of x is 0, then what I would have is that the AX plus BX is 0, and we already have the BX from the previous section, so we'll just substitute there, and then AX would be come out as 200 Newton, because we know that Bx is negative 200 Newton. So from the previous section we know it's 200, negative 200 Newton. So this is what we will get. And then if we write the sigma Fy is 0 for member AB, so we have the AY and it's a positive, and then we have BY plus BY is 0. And again, from the previous one, we know the By is negative 50, so the By is negative 50 Newton. So therefore, Ay would becomes out 50 Newton. And then to get the M, we can write the moment equation about point A is 0, and we consider this as a positive. So what we're going to do that, if you look at here, the M we consider is rotating clockwise, so we consider counterclockwise is positive, so the M rotates clockwise, so it's going to be negative M because it's rotating clockwise. And then AX and AY both go through point A, so they don't have any moment, they don't produce any moment. The BY is also go through the point A, so the distance is 0, it doesn't make any moment, doesn't produce any moment. The only forces that produce moment is Bx. So we have the Bx, and the normal distance between B and point A is 2 meters, as we have here, so it's times 2. And about point A, it is rotating it clockwise, so it's rotating it like that. So because it's rotating it like that, again, it's going to be clockwise, it's going to be negative, and it's going to be 0. And we already, again, we know that the Bx is negative 200 Newton. So we know that it is negative 200 Newton. And if we substitute there, then M would be comes out as 400 Newton meter. So when look at here again, the whole process of solving the frame is that, particularly if you have more unknown that you can solve, like here the reaction we have is more than number of elements we have, number of equilibrium equation. So just go ahead, disconnect each member, put all the external forces on members, then put all the reaction forces on the members, and then put all the internal forces on the members, and then start to write the equilibrium equation for each member. So for each member you can write 3 equilibrium equations, and you can find all the unknown. Remember that these internal forces, when we are dealing with the entire frame, when they are interforces, we don't care about, we don't bother about them. But as soon as we disconnect them, then internal forces becomes important. For that member, those internal forces behave as external forces, so we have to consider in our calculation. But when they are connected to each other, remember, like what we did before, as long as they're connected to each other, we don't care about the internal forces.